Okay, well, thank you, Keith and Alvaro, and the other organizers, for giving me the opportunity to speak here, and also for putting together what I'm sure is, for you, an unusual conference to put together. It would be nice to be able to see your university and see everyone in person, but on the other hand, there's something almost more comfortable about giving a conference talk, sort of in bare feet in my apartment. Okay, so before I get into it, I want to emphasize that this is all joint work with Leonardo Fiore, who was, he completed his master's degree at University of Milan, and I was his project supervisor during the last months that I worked at University of Milan. And towards the end of the talk, where the results get more difficult with genus 2, all of this more difficult stuff was mostly due to him, his results. Okay, so let's get into it. The main object of study for this talk is hyperelliptic curves over local fields. So first of all, in this talk, R is always going to be a discretely valued local ring with fraction field K, and the characteristic is always going to be 0. We're going to be thinking of this as generally the mixed characteristic case. So there is a maximal prime ideal and a residue field, and that has characteristic P. And you could think of P as also being 0 for some of the time in this talk, but we really want to be thinking of the 0P mixed characteristic case. And the main two situations which we will be comparing and contrasting are when P equals 2, as in the title and abstract of this talk, and when P does not equal 2, which I realize I should explain the situation when P is not equal to 2 as well, often first. Okay, so now we define a hyperelliptic curve. So this was defined in basically the same way in the talk before mine. So we're sticking with that definition, where a hyperelliptic curve is a smooth curve whose affine piece is just the set of solutions to an equation of this form, where y squared equals f of x, for some polynomial f. Where I'm going to differ from Wan Lin's presentation is that I am allowing the polynomial to be of degree as low as 3, right? So anyone who studied elliptic curves knows that when y squared equals a cubic in x, that's a standard equation defining an elliptic curve. So I'm considering an elliptic curve a special case of hyperelliptic curve, sort of it's the lowest genus case. And in this talk, mostly the more concrete parts of this, I'll just be treating the case of elliptic curves and the case of hyperelliptic curves of genus 2, where I'm going to assume that my degree of my polynomial d is just 5. Okay, so we'll make another simplifying assumption here. By the way, if you notice that as a simplifying assumption, this polynomial is monic. All right. So further simplifying assumption is these roots, which I label a sub 1 through a sub d of this polynomial, are actually lie in the ground field. So the ground field is the splitting field of this polynomial, let's say. And in fact, I'm even going to assume that they're integral, that they lie in R, which is not asking too much, because if they don't lie in R, if some of them were fractional or had denominators, there is a very simple denominator clearing trick. We can just scale x and scale y, and the worst we have to do is to pass to a quadratic extension of k. And in the context of this project, it's no problem to pass to finite algebraic extensions of k. So we can just go ahead and say that these are all integral. Now, let me just say a word or two about what it means for the curve to be smooth. But Wan Lin already covered this, right? So as she explained, the only singular points you could get in a curve in this form, at least when the characteristic is not 2, and remember this field has characteristic 0, right? The only way you could get singular points is when x is a solution or a root of the polynomial and y is 0. But not only that, it's when the x coordinate is also a root of the derivative of the polynomial. And this basically comes from considering that a singular point is going to be a point on the curve at which both partial derivatives vanish. And the partial derivative belonging to an equation like this, the partial with respect to y is 2y. And for 2y to vanish, since 2 is not 0, that means y must be 0. This is sort of the crucial thing that should be observed here, right? So because I said this is smooth, and therefore that's the same as saying that this polynomial has no multiple roots. All the a sub i's are distinct in K or R. All right, but then let's talk about reducing the hyperelliptic curve, right? So since we're over a local field, and in fact, all the coefficients are defined over the ring of integers, we can reduce them modulo the maximal p, right? And so we get this equation for a reduced curve where the coefficients are all in the residue field, and we can reduce all the coordinate points on the curve modulo p to get points defined over the residue field. And so now we have a curve over the residue field. And the interesting thing is that although we assumed that our curve originally, our upstairs curve, was smooth, and so all the roots of the polynomial are distinct, some of them might be equivalent modulo p, right? And so if they're equivalent modulo p, then you're going to see this, the curve defined over the residue field is defined by a polynomial whose roots are the reductions of the a sub i's. And some of those reductions might be the same. You get multiple roots. If the residue characteristic is not 2, then you know you're in trouble, and you have singular points on the reduction. So the reduced curve might not be smooth, even though the curve was smooth. We call this bad reduction. And when p is not 2, as I just explained, the singular points of the reduction are going to come exactly where we get several roots of the original polynomial, which are equivalent modulo p. We call such subsets of roots a cluster, right? So if there are no clusters, we have good reduction if p is not 2, but each cluster will give us a singular point. And if you have a cluster of exactly 2 roots, that's going to give us what's called a node in the reduction. So a node looks like this. This is sort of a standard picture of an elliptic curve with a degenerate elliptic curve, I should say, where 2 of the roots are equal, but the third one is different. And so it's where a curve is intersecting itself so that there are 2 tangent lines with 2 different slopes. But on the other hand, if you have a cluster of more than 2 roots, you get what we call a cusp, which you can see visibly, at least in a picture like this, where we're picturing everything over the real numbers, is a sharp point. It is not a smooth point. But the graphic doesn't really depict this. The tangent lines, there's only one possible slope of the tangent line. And we want to think of cusps as sort of worse than nodes. We want to think of nodes as like the mildest form of singular point, and cusps are sort of worse. All right, now this is all when p is not equal to 2, right? So when p equals 2, the situation is worse. Because now, if you try to solve for when the partial derivatives equal 0, the partial with respect to y, which I pointed out was 2y, solving 2y equals 0, well, now 2 equals 0, right? 2y is, so that's saying 0 equals 0. It tells us nothing about y, and any root of the polynomial with this reduced polynomial, or I should say any root of the derivative of this reduced polynomial will give us a singular point on the reduced curve. And moreover, it's not too hard to see algebraically. The singular point will always be a cusp. So no matter what, even if these reduced roots, the reductions of the roots are all distinct, you will always get singularities on the reduced curve, and they will always be the bad kind of singularity, not a node. All right. So let's make rigorous what we mean for reduction not be so bad. Bad, but not too bad. So semi-stable reduction of the curve over a local field means that its reduction over the residue field either is smooth, which means good reduction, or at worst it has a few singularities, but they're all nodes. And I mean, that could either mean a curve intersecting itself like this, like the picture I had before, or keep in mind that the reduced curve might have multiple components, but as long as they cross each other at sort of ordinary intersections, those are also considered nodes. All right. So at worst, it means at worst, not so bad. And so motivating result, deep result proven first by Deline and Mumford, then a different proof by Artin and Winters, I believe, which sort of motivates the whole project, is it says we can always adjust our curve somehow. Any curve that I give you over a discrete valuation field, even if its reduction has cusps in it, we can always do something to the equations of the curve to get an isomorphic curve, maybe over a finite algebraic extension of the ground field, so that that isomorphic curve, the reduction of that isomorphic curve has only nodes as singularities. So in particular, we should be able to do this with hyperelliptic curves, even in this sort of worst behaved case where the residue characteristic is 2. Now, this is a fairly easy exercise to see for elliptic curves when the residue characteristic is not 2, at least, because the only way you could have non-semi-stable reduction in the first place is additive reduction, when all 3 of the roots coalesce modulo p. And so there's a translating and scaling operation you can do to separate them. At worst, a quadratic extension of the ground field. So this, I think, could be a standard exercise for first semester elliptic curve students. And then for hyperelliptic curves in general, there are multiple 90-page papers, and at least 2 of them that I can think of by this research team, whose names I list up here. But they only treat the case when residue characteristic is not 2, and they treat a whole bunch of other things that we won't touch in this talk. But they show that the reduction type of the semi-stable model that you can get, what we call CSS, is determined entirely by how the roots of the defining polynomial cluster, meaning which subsets of them are equivalent mod p, but then within those subsets, which subsets are equivalent mod a higher power of p or are p-adically closer together. So I'll show you quickly how this works for genus 2. So I'm going to show that this is a matter of combinatorics, and this is not going to be exhaustive, but in the left column, I'm going to show different ways that the 5 roots, I've assumed the genus, the degree is 5, different ways that they can cluster. It reminds me of playing, I guess, a 5-card draw poker, right, where you have a hand of 5 cards. We're not going to think about straights or flushes or anything like that, just the numerical values. And you might have 2 of them the same number, 3 of them the same number, and it determines who wins the hand of poker, right? So in order of poker ranks, you can have a pair. So that's 2 roots equivalent mod p, all the rest distinct. You could have 2 pairs. You could have 3 of a kind, right? A cluster of 3, but no other clusters. Now we have a full house because we have 5 of them. 2 of them are equivalent mod p, and the other 3 are equivalent to something else, mod p. And finally, this does not happen in poker. I don't know whether it can be ranked higher or not. This is the most complicated case where 4 are equivalent mod p, but pairs of them are p-adically even closer to each other. And what happens for the reduction type of C in its semi-stable model is a pair is going to give us a node, like I said before. That's already semi-stable. We're good. We don't have to do anything else. 2 pairs gives us 2 nodes. Again, already semi-stable. Don't have to do anything else. 3 of a kind gives us a cusp, right? If you have more than 2 coalescing, you get a cusp. That's not good. But there's sort of a standard operation you can do to get an isomorphic curve where we've effectively blown up this point in the arithmetic surface. I'm speaking very roughly here. It's not precisely what you do, but instead of having this cusp, you get another component which crosses your original component at a node. And each component, these little numbers that I wrote here, are the arithmetic genus. Arithmetic genera of each component. So each component has genus 1, right? And that's semi-stable. House, similar situation, a node and a cusp now. but that cusp again can be turned into just another component which meets it at a node. And then, okay, this is going to be like a really bad cusp because 4 points came together. But this is sort of the least intuitive result here. You can actually get a model which is 2 lines of genus 0 meeting at 3 places, and at 3 nodes. All right, so the title of my talk in the abstract said p equals 2. So enough of residue characteristic not 2. Let's look at the harder case where p is 2. And let me talk about a general strategy for getting a semi-stable model when p equals 2. So the first thing you can do with y squared equals f of x, remember this is what we started with, you can translate and scale x. And also scale y in the process. And we call it alpha is the value you translate by, and beta is the value you scale by. They can be values in maybe values which are algebraic over k, right? And you choose some power over here, and you get a new variable y sub 1, whose square is a polynomial of x sub 1. This is a new polynomial. It might not have coefficients all in R now, and in fact, it shouldn't if we want this to work. And it might be that the coefficients of the highest order terms are actually in P, and then the reduction would actually lower the degree of the polynomial. That's okay, and we might do this multiple times to get different polynomials. What are we going to do with this? This was touched on, I think, in Arvin's talk, if I remember right, the sort of approximation by the square of a polynomial, where you can decompose your polynomial like this, right? And then you perform a simple variable change on y, and now you get, instead of something squared equals a polynomial with the other variable, you get this sort of linear term in the y variable as well. And this allows us to get away from the case where we're forced to have a cusp reduction. Okay, so really this makes more sense if you look at it backwards, if you think, well, this is the most general form of a hyperelliptic curve, and this is reducing the square.
Completing the square.
Sorry?
Completing the square. You have about
yes.
You have a couple of minutes. Yeah.
Oh, okay. Well, a bit behind where I thought. Okay, so with clever enough choices of alpha and beta, this is the real deep choice that we have to make, is what alpha and beta are. There's sort of a straightforward algorithm to get this, as Arvin mentioned. And you should, in theory, be able to get something that reduces to a semi-stable curve. Okay, so because I'm low on time, I'll breeze through this very quickly. So you can see on the recording, here's what this slide looks like. It's a simple situation for elliptic curves. It depends now on how p-adically close the 2 roots that cluster are, which it did not before when p was not 2. Let me get to the new results that mostly Leonardo figured out, where now even no cluster does not necessarily give you a smooth curve in the semi-stable model or a smooth reduction. It could, or it could give you this 2 elliptic curves meeting at a node. A pair gives you these complicated 4 cases, which you see there are more nodes from the curve intersecting itself when the distance, the p-adic distance between the 2 roots is greater than 4. We saw something similar with elliptic curves. Luckily, it becomes simpler after this. With 2 pairs, you always get 2 components of the arithmetic genus 1, and whether each one has a node on it depends on whether each of these p-adic distances is greater than 4 or not. So you get these 3 possibilities. Let's move on to 3 of a kind. Exactly the same thing happens as when the residue characteristic is not 2, except that the thickness of this node will be greater. But that's sort of a more minor point. Full house, pretty straightforward, always 2 components. And one of them has a node if and only if the p-adic distance between these 2 roots is greater than 4. And then finally, the only case where we haven't completely figured out all the subcases, but let's just say that if everything is p-adically close enough to each other, you get the same picture of 2 genus 0 lines intersecting in 3 nodes. that we got when residue characteristic was not 2. Okay, so those are the results I wanted to show you. I don't want to go too far over time. So I think I'll just say thank you.
Okay. Thank you.